Okay, so hi guys, my name is Aditya Ramesh. The concept that I'm going to teach you guys about today is known as quantum entanglement. Now, before I can teach you guys about quantum entanglement, I would like to teach you guys about this concept known as wave function. So now, let us consider that there are three steps over here. We will name them as A, B, and C. So here on the ground we have Sal Khan, who is standing and who is facing in the opposite direction from the steps. So now Sal has a ball in his hand which he's going to throw backwards at the steps. So now there is equal probability that the ball will fall on steps A, B and C. So now until the time that nobody observes this system, I can say that this system is in a superposition state wherein the ball is on steps A, B and C at the exact same point of time. Now let me say that Sal turns and he observes the system. At this point of time, the wave function will collapse from being a superposition of all these three to just being the ball on step A or the ball on step B or the ball on step C. So this is known as the collapse of wave function. We'll be using this later on while we're dealing with quantum entanglement. So what exactly are entangled particles? Any two particles which are produced spontaneously as well as simultaneously from energy can be considered to be entangled particles. So now I just produced energy, right? I just produced sound energy from the board by hitting the board with my hand. Let me assume that along with the sound energy, there were also two electrons which are formed. So electron number 1 and electron number 2. Right. So now there is a fundamental property of an electron known as spin. Now spin is basically an analog of the angular momentum and magnetic moment of an electron measured in a particular direction. So now let me take the direction of measurement to be up. Okay. Before I measure the spins of either particles 1 or 2, we know that the spin is in a superposition of up spin and down spin. So now let me measure that of spin of particle 1. Let me say I've already done this experiment, so I know that the spin of particle 1 comes out to be down, and let me do it for 2 also, and since I've already done this experiment, it comes out to be up. Alright, however, it is absolutely not necessary to do this experiment for particle number 2 because these two particles are entangled. Now here comes the cool part. A change in the spin of particle 1 will cause an equal and opposite change in particle 2. This is super cool, okay? Because if I were to change the spin of particle 1 to up, instantly, the spin of particle 2 reverses and becomes down. So now, even if I were to separate them to opposite ends of the universe, so this is, let me say, end A and this is end B. Even if I were to do that, and again I reverse this, now I make this one down, this one again reverses and becomes up instantaneously. Now if I were to draw the probability chart for 1, 2 and probability percentage for their spins, right? So now theoretically it comes out to be up, up, down, down, up, down, down, up, each having 25% probability. However, according to what we've just learned, a change in one produces an equal and opposite change in the other. So I can say that these first two scenarios are not possible and can be ruled out. So the only two possible outcomes are these two, which is up, down and down, up, each having a probability of 50%. Alright, so yeah, that's it about quantum entanglement, and thank you, and I hope you enjoy watching the video.